Actually going to start by kind of like reviewing what we discussed last time, talking about these quantities that are going to be really important in this particular chapter. Hydronium concentration, hydroxide concentration, pH and pOH. All right, there's a really intimate relationship between these four quantities here. We sort of discussed this last class period, but I got like this little graphic that we're going to make that kind of helps summarize that and put it in our brain a little bit better. All right, so this is now talking about our relationship between hydronium concentration, hydroxide concentration, pH, and pOH. Okay, so first of all, hydronium and importantly, what the important part to sort of note about this is if you know any one of these about your solution, if you know what its hydronium concentration is, then you can find hydroxide, pH, and pOH, right? If you know one of these, you can find all the other three. All right, so first of all, hydronium and hydroxide. All right, we can convert between the two of these using what we call the auto-ionization relationship, that equilibrium that exists when water reacts with itself, all right, where our hydronium ion concentration plus our hydroxide ion concentration always equals, or rather multiplied by my hydroxide ion concentration, always equals that same magic number, 10 to the negative 14, what we call our Kw. All right, we also said that we can convert hydronium ion concentration into what we call the pH of our solution. And pH is really how we like to talk about these. That's kind of our default go-to quantity. Rather than talking in units of concentration, we talk in pH. And our formula for that was that our pH is the negative log of that concentration of hydronium. All right, likewise, we can go the other direction by using the inverse of this equation here. That would be hydronium concentration is equal to 10 to the negative pH. All right, and then we also talked about pOH, sort of the analogy, but now talking about hydroxide concentration. So we can convert from hydroxide concentration into pOH by using the same formula. pOH is the negative log of the concentration of hydroxide. Or we could go back using again the inverse. Hydroxide concentration is 10 to the negative pOH. All right, and lastly, we can relate pH and pOH using that same auto-ionization relationship, but putting it on a log scale. All right, that's what we did at the end of last class period. We took the negative log of both sides of this equation here, and we found that that simplified to pH plus pOH equals 14. All right, so importantly, if we know any one of these, if we start on any one of these corners here, we can find all of these other quantities, right? They're intimately related for your solution, for all aqueous solutions. Cool. All right, so then we started talking about these acid dissociation reactions, all right? This is where we take our acid and we put it into water. Since water is playing the role of the base there, we always get hydronium as one of our products, and then whatever our conjugate base is. All right, so let's just review here. All right, write that acid dissociation reaction. For HI. so we're going to take this HI, we're going to put it into water. My HI is my acid, my water is my base, so in order to get my conjugate acid formula, I'm going to take my base, water, and I'm going to increase the number of hydrogens by 1 and increase its charge. That's why we always get hydronium as a product here. And then for my conjugate base, I'm going to do this opposite. I'm going to look at my acid formula, and I'm going to decrease the number of hydrogens and decrease its charge. All right, and just to be good, as we said, this is the acid and this is the base. I want you to label our products here. What's the conjugate acid and what's the conjugate base? Remember, our base tells us the formula for our conjugate acid. And our acid tells us the formula of our conjugate base. All right, and that seems kind of backwards that the base and the conjugate acid and the conjugate base are related. But remember, we've updated our way of looking at reactions, and we don't just look at them going in one direction. Now we know that they can go in both directions. All right? That said, this reaction right here, we would say goes 100% to completion. All right? We would not worry about the equilibrium arrows for this one. We would just use this one directional arrow here. And that's because hydroiodic acid is one of our 6 strong acids. All right, there are 6 strong acids. We just got to know them. All right, these 6 here. If it's not on this list, it's not a strong acid. But these 6 are our strong acids. And remember what it meant to be a strong acid. All right, in terms of our pH calculations, this is actually going to make our lives a lot easier. If we have a strong acid, that's kind of best case scenario. Right? That means that our concentration of our strong acid, whatever we start out with here, 100% of it is going to dissociate into our conjugate acid and our conjugate base, meaning whatever I start out with this, however many molecules of hydroiodic acid I have, that's how many molecules of my hydronium will be created. All right, so for our strong acids, we said the concentration of that strong acid that we have initially is going to be equal to our concentration of hydronium when this reaction reaches equilibrium. Right? Another way of saying this reaction goes 100% to completion. Okay, so then let's finish this problem off here. You're going to calculate the pH of a, say, 0.0463 molar solution of HI. So my concentration of HI that I prepared this solution with is equal to that 0.0463 molar, but I know that's also my concentration of hydronium when this reaction reaches equilibrium. And since I know my concentration of hydronium, I can just go ahead and use our definition of pH, negative log of that hydronium ion concentration, plug it into my calculator, 1.334419, etc. We talked about units for pH. What are my units here? Yeah, trick question. No units on pH. It's a unitless quantity. All right. The last thing that we talked about was our significant figures for our pH. My concentration here has 3 sig figs. So that means I need 3 what in my pH? Decimal places. All right. So 3 sig figs means 3 decimal places when I calculate my pH here. Okay, so my final answer, pH equals 1.334, no units, put a box around it. Okay? Cool. All right, so we're going to go back to this acid dissociation reaction to talk about all the other acids in the world, right? We know how to deal with those 6 strong acids. What about all the other ones? But first, we're going to take a turn and start talking about bases. And in particular, we need to define an analogous base dissociation reaction. Our base dissociation reaction is when we take a base and combine it with water. All right, which means water's playing the role of the acid in this reaction. Okay, so let's take a look at some base. We're going to mix it with water. All right, and everybody's going to take a second and draw me the products of this reaction based on what we discussed last class period. Remember, our base, we're going to add a hydrogen. The base is the proton acceptor, so that means my formula here should be NH4, and it increases the charge. So increase number of hydrogens, increase my charge. All right. I'm going to take my acid, I'm going to decrease the number of hydrogens and decrease its charge. So we see that in these base dissociation reactions, because water is playing the role of the acid, we will always get that hydroxide ion and whatever your conjugate acid is. All right, so when we combine an acid and water, we get hydronium as our product. When we combine a base and water, we get hydroxide as our product. All right? Now, this reaction, again, is what we're going to be concerned about for talking about acids and bases. They have this equilibrium constant K, and because it's this specific base dissociation reactions, these are denoted Kb. All right, that would be the equilibrium constant for this reaction. Cool. And just like we had this concept with strong acids, we also have this concept with strong bases. A strong base means that Kb is very large. All right, a Kb value that's very large means that it would strongly favor the products. All right, and that value for Kb is so large that we don't even treat this as an equilibrium problem. We look at this reaction and say it goes 100% to completion. All right, so for our strong bases, our dissociation reaction goes 100% to completion. Truthfully, there are a lot of strong bases out there, but you'll see a lot more of them when you get to, say, organic chemistry. For our purposes, in terms of spying our strong bases, what you need to look out for is a soluble compound that contains hydroxide. All right? So our strong bases are soluble ionic compounds with hydroxide. All right, so just some examples. One of them I'm positive you've seen in the lab before. The most common example would be sodium hydroxide. But I could pair that hydroxide ion with any one of those group 1 metals. So another one that I could use would be potassium hydroxide. That would also work. Okay. There's also, we could pair it, most of the group 2 metals are actually not soluble with hydroxide, but there is an exception, and that's barium hydroxide. All right, since barium's got a +2 charge, there has to be 2 of those hydroxide ions. So we're just going to note this will dissociate into 2 OHs. All right, so again, we have this base dissociation reaction. We're going to talk about this equilibrium. We're going to do a bunch of equilibrium problems with this reaction here. But if we have a strong base, something that's classified as a strong base, we don't have to worry about the equilibrium of this reaction. We just say it goes 100% to completion. All right? Similarly, like what we did for our strong acids. So let's just ask here, what is the pH of a 0.0463 molar solution of sodium hydroxide? All right, so first of all, how are we going to go about this? Well, we know our sodium hydroxide concentration, that's what we prepared, is equal to that 0.0463 molar. But since that's sodium hydroxide, 100% of it is going to dissociate into sodium ions and hydroxide ions. That means that's also my concentration of my hydroxide once it's dissolved. All right, now, let's make some room here. Done a bunch of these pH problems before. So everybody's going to their calculator and they're going to say, all right, the negative log of that 0.0463, spit that out, 1.33441. All right, and I'm done. No, because what did we just calculate here? The POH, right? Because I was plugging in hydroxide ion concentration. This isn't simply the pH, but rather the POH. Now, we're still making our way there, all right? This is perfectly fine because I can convert POH into pH using that log of our auto-ionization relationship, right? I can just take the fact that my pH plus my POH equals that number of 14. We just got to remember what we calculated wasn't pH, but rather POH, and then we can plug it into this formula here, right? So I'm starting here. I need to make my way over here, right? So first we did our negative log to get our POH, and then we're going to convert to pH using that auto-ionization relationship. Likewise, I could have also gone the other way. I could have taken my hydroxide ion concentration and first use my auto-ionization relationship to convert that into hydronium, and then taken the negative log, right? But the bottom line is we're going to start here. We need to somehow make our way over here. And we could have chosen either path, and we would get the same answer. All right? Since I already did the work to be in POH, let's just go from here. We're going to take our pH plus POH equals 14. And if I rearrange this pH, that means I do 14 minus that POH. All right. And I get 12.665580. That's cool. All right, and then lastly, because I want to make sure I get full credit on my exam question, what am I going to do as my last step? Sig figs, all right? And again, my number of sig figs, my 3 sig figs in that concentration corresponds to 3 decimal places in this log space here. So my final answer, 12.666. Lucky number. Okay? It's not 5 sig figs. So this number, if you look at it, has 5 sig figs. But importantly, the rule is our number of sig figs here corresponds to our number of decimal places. So how many digits I have after my decimal in that pH space. Okay, cool. So we talked about strong acids and strong bases. So what about every other acid and base in the world? How are we going to deal with that? All right. So let's just take an example here. What is the pH of a 0.25 molar solution of acetic acid? C3COOH. All right, so acetic acid is the active ingredient in vinegar. It smells just like vinegar, and it is a weak acid. All right, so step 1, how are we going to go about doing this problem here? Step 1, we're going to write that acid dissociation equation. All right, we're going to take that weak acid, we're going to mix it with water, and we're going to get that conjugate acid and our conjugate base. Our conjugate acid specifically would be that hydronium. right, so remember our acid is going to lose a proton. Which hydrogen am I going to take from? This first one or the last one? Yeah, so they're all, the donatable hydrogen's always listed either first or last. So I'm not going to touch these three here. I'm going to remove the last one. Right, and then my water accepts that proton, becoming the hydronium ion. This is our acid dissociation equation. Because it's that special acid dissociation equation, this has this equilibrium constant Ka, right? We give it the little a because it's an acid dissociation equation. All right, so now we're going to write our equilibrium expression. All right, so these weak acids here, and maybe I should have titled this here. Let's throw a title on this section here. Now we're talking about weak acids. All right, and because this is a weak acid, we can no longer assume that this reaction goes 100% to completion. All right, this is now going to be an equilibrium problem. So we're going to need to write out our equilibrium expression here. Our equilibrium expressions, what do we remember? What over what? Products over reactants. And which one of these things from my balanced chemical equation do I get to omit? The water, because it's got that liquid designation. So products over reactant, omitting that water. I also have to remember that my coefficients become exponents, but fortunately for us, these acid-base equations will always be 1 to 1 to 1 to 1. Okay, so now I'm asking for the pH of our solution here. So in my equilibrium expression, what do we think we're going to be trying to solve for in order to get to the pH of our solution? If we know this, if we know our hydronium concentration, then we can figure out the pH of our solution, right? So this is what we're going to be solving for, is solving for that hydronium ion concentration, all right? So I need a little bit more information before I can do it. These Ka values for all of our weak acids that we're going to study are tabulated on our constants page. All right, so we got a big constants page here. These are all of our weak acids. And so what I'm going to do is I'm going to find my weak acid, acetic acid. All right. And then I have my value for that Ka as well. All right, so 1.8 times 10 to the negative 5. So we're just going to note that here. So we know the value of our equilibrium constant. All right, we have our equilibrium expression here. And last chapter, we learned a particular strategy for how we go about solving these equilibrium problems. What did we use for that? Somebody said it. What kind of table? The ice table, all right? And again, that's going to be our same approach here. We have another equilibrium problem on our hands, just within this specific context of acids and bases. So we're going to build an ice table. All right, so given what we discussed last time, everybody take a second and build me an ice table. What's up? Because that's the value that I looked up on my constants page. Oh, you just looked that up. I just looked it up, yeah. All right, so I got my ice table here. What is my initial concentration of my acetic acid? 0.25 molar, that's what my problem told me. All right, and how much product do I have at the beginning here? None. I don't start out with any product here. All right, now let's note that this is a little bit of a lie, because if I'm starting out with neutral water here, what is the concentration of hydronium in there? For that neutral pH, remember, pH 7, if we want to work backwards, this should really be 10 to the negative 7. But it turns out that that is such a friggin' teeny tiny number that it will not impact our calculation to just assume that it's 0 to start out with. There are some rare circumstances where that's not the case, but generally speaking, and for all the problems that we do, we can just assume there's no hydronium at this point. Not yet, at least. All right, what goes in our change box? That variable. So we're going to put an X in here. And we got to remember that our reactants are going to decrease in concentration and our products are going to increase in concentration. So we have the sign of X is different for these different boxes. All right, and then lastly, our E box here is where we sum everything up. So 0.25 minus X, X, 0 plus X is X, and 0 plus X is X again. All right, now we're going to take what we just solved from our, rather what we just built in our ice table and plug in to that Ka expression. All right, so if we take our equilibrium expression here, my equilibrium concentration of that acetic acid is 0.25 minus X. Our equilibrium concentration of that conjugate base is X. And what I really care about, my hydronium ion concentration here is also X. All right, so we're going to take these and plug them back in to that expression up there. Ka equals X times X over 0.25 minus X. And again, where did these come from? They came from our ice table. That 0.25 minus X was my concentration of my acetic acid at equilibrium. X is the concentration of both my conjugate base and my hydronium at equilibrium. All right. So we all see where we got our equilibrium expression from our balanced chemical equation. We then built our ice table, and now we're plugging these in to our equilibrium expression, back into that expression. Because I know that this all is equal to that 1.8 times 10 to the negative 5 value. Okay. We could algebra this to solve for it, or we could make our lives a lot easier by using the solver feature on our calculator here, all right? But there's another way that we can go about this that works quite often, not necessarily every single time, but quite often. And that is what we call, all right, so let's actually just title this here. This is solving for X. All right, method 1, you can use that solver. All right, I'm going to have certain homework problems where you're going to be forced to use your solver here. All right, so remember, I showed how to do it on my calculator. I'm happy to help you try to figure out how to do it on your calculator. And importantly, there's that website that everybody has access to that you can use as well for your homework. All right, so that'd be method 1. We could punch this into our calculator here and get that value for X. But there's another method that we can use, which is called the small x approximation. All right, so what is this small x approximation here? First of all, let's note the value of this equilibrium constant, 1.8 times 10 to the negative 5. What does that say about this reaction over here? Does it favor the products or the reactants? The reactants. And does it weakly or strongly favor the reactants? Strongly. So this reaction does not happen very much at all. right? Only very little of that acetic acid is actually going to dissociate into our products here. So there's very little reaction that occurs, meaning our value for X is going to be some teeny tiny number, all right? That's true for most of these weak acids. They have these low Ka values, meaning that those reactions don't favor the products, meaning that your value that you're going to get for X is going to be a small number, all right? Now, because of the log scale, that still has a big impact on pH, but nonetheless, very tiny number here, all right? So I'm going to rewrite my Ka expression here. All right, I'm also going to combine the, what is x times x? That's just x squared. I'm going to simplify. Okay, and my small x approximation says that since x is so small, right, this is some tiny number, that means that my denominator, that 0.25 minus x, is basically just 0.25. All right, so our equilibrium expression here will simplify to simply x squared over that initial concentration. This teeny tiny number doesn't change the value of the denominator very much, so I'm just going to ignore it. All right, and the reason why we do that is because now we have a much easier algebra problem on our hands here, okay? So everybody take a second. Given this small x approximation, I want you to calculate the pH of this solution. All right, so I get 1.8 times 10 to the negative 5 equals x squared over 0.25. If I'm solving for x, what's the first thing that I'm going to do? Multiply both sides by 0.25. So now I have x squared equals that 1.8 times 10 to the negative 5 times that 0.25. And if I'm going to solve for x, what do I need to do both sides? Square root. Okay, so x is the square root of my Ka times that initial concentration. All right, now I don't want to break anybody's heart here, but because this is now this ice table problem, it involves this square root, we're not going to worry about sig figs here. All right, so your homework will tell you how many digits to enter in for your particular answer. Okay, and I'm done. No, because my x here is what? What did I just solve for when I solved for x? My hydronium ion concentration, but what I'm asked for is my pH. So I got one more step here. I got to take the negative log of that value of x. My pH equals the negative log of x equals, what is it? We'll say 2 decimal places, 2.67. right, so this small x approximation, we can just note we assume x is small and remove it from the denominator. All right, but then we got to double check. We got to double check this small x approximation. All right? And that is, well, so we're going to just say check our small x approx. All right? Your small x approximation is valid if the ionization, the percent ionization rather, is less than 5. Okay, your percent ionization is how much of that dissociation reaction occurred. So it's the amount of hydronium at equilibrium divided by the amount of acid that you had initially made into a percent, so we're going to multiply it by 100. All right, we're going to have an analogous sort of thing for our bases as well, so let's just note, if we were talking about a base, we'd be talking about our hydroxide concentration at equilibrium divided by that initial concentration of base times 100. All right, these are our percent ionization, how much of that reaction has actually occurred. Okay, so in order to check my small x approximation here, I'm going to take that value that we got for x, our concentration of hydronium, and I'm going to divide it by that initial concentration of my acetic acid, multiply it by 100, and that number better be less than 5. Okay, so just to finish this problem off here, we're going to take our 0.002121 divided by that initial concentration of 0.25 molar, multiply all this by 100. We get 0.84, let's call it 0.85%. So did we pass? Cool. All right, so we pass. Okay, let's just note that if we fail, that means you have to use the solver. You can't use that small x approximation to simplify your algebra. You got to use your solver. You don't have to use your solver. You could actually just rearrange this equation, but it's a quadratic, so then you'd have to use the quadratic formula. It's kind of just a pain in the butt, all right? But the bottom line is you would not be able to drop that x and get away with it. Okay? Cool. So when we're talking about our weak acids here, we're talking about the pH of this solution of weak acid, we're really talking about an equilibrium problem, where we're going to have to calculate how much product is formed when this reaction reaches equilibrium. What's up?
Are there going to be any questions on our test like that where we would have to use a solver?
Yeah, good question. So no. On your exam, I'll make sure that you can use your small x approximation. You should know how to check it and everything like that, but I'm not going to assume everybody has a calculator with a solver on it. On your homework, you can expect to be forced to use it, right? You can expect to be forced to use your solver. Cool. Okay, one more thing about this Ka table here. Again, this is our constants page. We got a list of a whole bunch of acids here. Okay, let me just pick up one. Let's look at phosphoric acid. All right, phosphorus acid. I lied. Let me pick it. There it is. Phosphoric acid. Notice that there are 3 Ka values associated with this particular acid. All right, so why is that? Because this particular acid has 3 donatable protons. So it's got 1 Ka value for its first proton, another Ka value for its second proton, and a last one for its third proton, right? Each one of these, and you can see they decrease in our Ka, meaning removal of the next proton is always less favorable than the previous one. All right? So, importantly, what this means is if I was asked to calculate the pH of phosphoric acid, HPO4, I would want to use that Ka1, that first value listed. All right? But if instead I started out with that having already lost a proton, then I would be using my Ka2 value, or if I was talking about that last proton, I would be using that Ka3 value. All right, so for these polyprotic acids is what they're called. Acids that can donate multiple protons. They have multiple Ka values. You're going to use whichever one corresponds to the correct state of that molecule that you're given. Cool. All right, so we talked about weak acids. Where are we going with this here now? We're going to go to weak bases. And if we scroll down on our table here, just like we have these Ka values for our weak acids, we also have Kb values for our weak bases. All right, so we have a bunch of bases listed here as well. Okay, we wrote previously we had done our balanced chemical equation for ammonia, so let's go ahead and take this one here. 1.76 times 10 to the negative 5. Ammonia is a weak base, yeah. Okay. Ammonia is a weak base. Remember, the strong bases all have that hydroxide in them. Okay. Where am I at here? Okay, so we had talked about this base dissociation reaction. So I'm just going to copy this chemical formula here. Okay, now we're talking about weak bases. Okay, and given what we discussed previously, I want you guys to see if you can answer the following question for me. What is the pH of a 0.25 molar solution of ammonia? Okay, and we're going to do the same thing. We need our chemical equation. We need that Kb expression. And in order to solve that Kb expression, we're going to create an ice table. All right, so I'm going to give you guys a bit of a head start, and then I'm going to kind of quietly start filling in up here. If you get stuck, you can look up, but based on what we've discussed up until this point, I believe in y'all. See if you can tell me the pH of this solution. What's up? Correct. Be careful with your signs, though. Your signs are going to be dictated by what are reactants and what are products. Reactants decrease in concentration and the products increase in concentration. Since that's a reactant, that means that that one's going to go down. But these two are products, so they both are going to go up. All right, so I got my ice table built here. I'm now going to go ahead and plug everything back in to my equilibrium expression. My 0.25 minus x in my denominator, x times x in my numerator. And again, the value that we looked up here is that 1.76 times 10 to the negative 5. All right. For the sake of variety here, let's go ahead and use our solver feature. Try to make some room so we can see. All right, I'm going to punch this into, well, I guess let me finish plugging these in. KB equals x squared over my 0.25 minus x. That's what I get when I plug these in from my ice table. Cool. All right, so again, I'm going to go to my numSolve feature here. All right, let me just get rid of this here. I got my one side of my equal sign. I'm going to put that KB value in, 1.76 times 10 to the negative 5. All right, and then over here, since I'm going to do my real x, right, not going to do the small x approximation, I'll have x squared divided by, and I'm going to put parentheses so it keeps in the denominator, whoops, just 0.25, not 0.025, minus x. All right, so now I have to give it this seed value here. And based on that KB value, what do I know about x? Is it going to be a big number or a little number? It's going to be a little number, right? So now I want to seed it with a little number. So I'm going to put in 0.0001, some small number, right? So now that this reaction is not very favorable, we don't want to put in a big number. That's going to be far away from our answer. It's going to make your calculator take forever, or it's going to throw you an error because it's too far away. So I'm going to put in this little number and then have it solve for x. All right, give it a second here, and it returns this value of 0.002088, whatever. All right. All right, I'm just going to say we used the solver here, and we found our value of x to be 0.002088. Just throw down a bunch of extra digits here. Okay? So now I'm going to take the negative log of x, just like we did last time. And I get 2.680, and I'm done. No, so why not? Why am I not done yet? What did I just calculate? The POH. Remember, your x in this case, because we're talking about a base, is hydroxide concentration, which means that we just calculated the POH of this solution at 2.68. All right? So we can find from here our pH, that 14 minus your POH. All right, so the pH of this solution here is 11.32. All right. The other thing is we want to do like a little bit of a sanity check. Let's say that I stopped, I got this pH of 2.68. Why would that not make sense for this solution? For a pH of 2.68, what would we classify that solution as? Acidic. And what do we just put in water? A base. So you're not going to get an acidic solution when you put a base in there, right? So a little sanity check can help you prevent you from making some silly errors here. But yes, I should have a basic solution for my solution of base. All right, pH above 7. Okay, last one here. All right, this is going to be the pH of our conjugate acid or base. Okay. So let's say, what is the pH of a 0.25 molar solution of fluoride ions? All right, so first of all, fluoride in our acids and bases chapter here. Would this be an acid or a base? How do I know it has to be a base? Yeah, Yeah, it doesn't have a proton to donate, right? So in this case here, it couldn't possibly play the role of an acid. It turns out that fluoride is a weak base. All right, so noting that this is going to be a base, give me my base dissociation reaction. All right, my fluoride ion, put that in water. This will dissociate into HF and hydroxide. All right, my water playing the role of the acid. It's going to donate a proton, so its formula is going to go down one hydrogen and decrease in charge. All right, and as we said, this was a base, so here's my Kb. So everybody's going to take a second and give me my Kb expression. What's up? So my base is going to accept a proton, so I go up in number of hydrogens and my charge goes up by one. My acid is going to donate its proton, so I go down in number of hydrogens and my charge decreases by one.
So bases gain and acids.
Yep. Acids are proton donors, so they lose a proton. Bases are proton acceptors, so they gain a proton. All right, so I get my Kb equals that concentration of HF times hydroxide concentration, all divided by that fluoride ion concentration. And we're going to look up that value for Kb. So we go to our table here, and we're going to stare at this for forever, and we're going to find no fluoride ion listed under our Kb values. All right, so if we look carefully here, we do not see any fluoride ions. Instead, what we see, if we look up here, is under the acids table, hydrofluoric acid with a Ka value given. Close, yeah. So we're going to have to figure out what our Kb value is from this here. What's listed is this acid dissociation constant for hydrofluoric acid. So let's go back here. We said we weren't talking about hydrofluoric acid, we were talking about fluoride, but nonetheless, let's do our, so this was for our base. All right, we're gonna play the same game here, but we're gonna do our acid chemical equation. All right, where we take HF and we put that in water. This has that Ka value that we know, that we looked up on that table there. And this will create hydronium and those fluoride ions. If we do our Ka expression, products over reactants. Why did I I lost it. All right, everybody take a second, do the Ka expression while I try to find this. Where the heck did it go? It literally disappeared. Okay, whatever. Okay, so quickly. Okay, and then if we did our acid, HF plus water, it's Ka, we got fluoride, hydronium. So if we do our Ka expression, okay, sorry. Okay, so importantly, what I know based on my constants page is this value here, my equilibrium constant for my acid dissociation reaction. And what I don't know is my equilibrium constant for my base dissociation reaction. But these two turn out to be closely related to one another. All right, so let's say our relationship between Ka and Kb. All right, what I want you to do is to take that equation for Kb and multiply it by that equation for Ka. All right, by that I mean I'm going to take my expression for Ka and I'm going to multiply that by that expression for Kb, and I want everybody to take a second and simplify this equation here. Right, so I got my form, my equation, my expression for Ka, and I'm multiplying that by my expression for Kb. And can I simplify this at all? Yes. What's going to cancel? Yeah, so my fluoride ions cancel out, my hydrofluoric acid concentration cancels out, and so what I'm left with is hydronium times hydroxide, right? That's what Ka times Kb is. But what's hydronium times hydroxide? That 10 to the negative 14, right? This is this Kw expression here, our autoionization. So we know that Ka times Kb equals that Kw, that 10 to the negative 14. All right, so this is our relationship between Ka and Kb. If I wanted to figure out what my Kb was for this particular acid, for my fluoride ion, I would look up my hydrofluoric acid, Ka value, and then use this equation here to solve for Kb, right? So to be clear, rearranging this here, we get Kb equals 10 to the negative 14 divided by Ka right, by rearranging this equation. So if I go here, I go here, my hydrofluoric acid, my Ka value is 6.8 times 10 to the negative 4. If I wanted my Kb value, let's see if I can freaking find it. I would do 10 to the negative 14 divided by 6.8 times 10 to the negative 4. Okay, this is equal to 10 to the negative 14 divided by that Ka value for hydrofluoric acid. Ten to the negative 14 divided by, what was that value again? 6.8 times 10 to the negative 4? Yeah. And then I'd be ready to go building my ice table and plugging everything in to solve for my hydroxide concentration for my weak base here. All right, so the important thing that we want to note here is our Ka times our Kb, let me just clean this up a little bit, is equal to that magic number Kw, that 10 to the negative 14. All right, and we're just going to note that this is specifically for conjugate pairs. Cool. All right, we're done. We will pick up with this next time.